All right. The next particular topic is going to be about latent heat. We've already talked about specific heat, and specific heat is really about raising the temperature of a particular object. Latent heat is more in reference to changing the physical state of a particular object. So right off the bat, just what we mean when we talk about changing states is like going from a solid to a liquid, or a liquid to a gas, or even a solid to a gas. Okay, so I've written those terms on here, and I'm going to assume that you're aware of what those are. But one thing that to keep in mind is that during a phase change, the temperature of the object actually remains constant. If you've got ice in a glass, the temperature of the water and the ice should be the same until all the ice has changed into liquid. During that phase change, the temperature should remain fairly constant. Okay. Now, this is because energy is actually needed to make the molecules themselves move around faster. And in every state of matter, the molecules are moving faster. So to go from a solid to a liquid, you need to give it energy to break those bonds apart so that the molecules can move a little more freely. Okay, so there's an analogy, and it's an okay analogy. It's called the ball in the box analogy, where if you've got a molecule and it's moving back and forth in the box, then it has kinetic energy. Okay, now if it's only got a fixed path and it can only really go back and forth and back and forth and back and forth, if I add some energy, we're going to say that because it's so close in here, it's not going to go faster. Okay, but what we can do is we increase the potential energy, so it has the more potential and the same amount of kinetic because we've added in some energy. Okay, we're heating it up. Okay, we continue to add heat. Okay, and again, the ball eventually gets enough potential energy so that it gets out of the box, and now it's free to move. Okay, so this would represent being a solid, still a solid, but giving it more potential, and boom, now it's a liquid and it's free to move around. Okay, so it still has the same kinetic energy. In these cases, all these velocity vectors would be the same, but now it has potential energy and it's able to move, so it's physically changed states. Okay. So a couple things that we should make sure that we clarify is the difference between boiling and evaporation. Okay. If you look at my basic definitions here, it says boiling takes place throughout the liquid and always at the surface, or I'm sorry, and always at the same temperature, where evaporation takes place only at the surface of a liquid and can happen at all temperatures. I mean, really, water evaporates no matter what temperature it is. It can evaporate. So this is a picture. This is the surface of, say, a liquid. You got some atoms in there that are moving around. Some of them could be moving faster than others. Okay, those fast-moving molecules, if they're close to the surface of the liquid, they might have enough speed to actually get away. Okay, so it says right here, some of those fast-moving surfaces can leave the surface. If that actually happens, the liquid as a whole is going to cool down. Evaporation is an endothermic process. It does cool things down. It's kind of like when you sweat. Why do you sweat? Well, that liquid on your body evaporates and cools your body down. It's a mechanism to keep your body at a cool temperature. Okay, you can affect the rate of evaporation a few different ways. Number one, you can increase the surface area. Okay, so if you had something in a cup as opposed to, say, in a dish, the dish provides more surface area. It allows more molecules the opportunity to be on the surface. The second one, I think, is a no-brainer, and not necessarily this term. It says remove the vapor cloud. Well, why do people blow on your coffee? Well, you get like some vapor on the top that kind of holds stuff in. If you get rid of the vapor cloud itself, it allows more molecules to escape, essentially. Okay, so that's why people will blow across something that's hot. You're getting rid of the vapor that's kind of keeping the heat in a little bit. By getting rid of it, it allows more to escape. And then the last thing you can do is obviously heat the object up. Okay. All right, so now let's actually get into specific latent heat. So I've given you a definition here that says specific latent heat, which gets the symbol L, of a material is the amount of heat required to change the state of 1 kilogram of the material without changing the temperature. So this one leaves the temperature out. We've got units of joules per kilogram, and I was just going to kind of talk about what latent means. Latent really has kind of a meaning that means like hidden, or sometimes it's easy to think of lazy, because really nothing's changing. The temperature isn't changing, however the state of matter itself is changing, okay, but no increase in temperature. So I've given you the formula right here. Latent heat is equal to the amount of energy divided by the mass, and this is simply for changing the state of it. Now, I've also again drawn a picture, and this one's also on the top of the web page for this unit. Going from a gas to a liquid is referred to as the latent heat of vaporization. Going from a liquid to a gas is the latent heat of vaporization. Going from a solid to a liquid, or liquid to a solid, is the latent heat of fusion. And then from solid to gas, or gas to solid, is called the latent heat of sublimation. Okay, so you might see LV, LF, LS. You might see those things. It's just referring to which states are changing. Okay, so I thought I would show you a graph. Okay, and this is a graph of temperature versus time. Okay, and this, we could say this is for something melting. Okay, this particular line right here, where the temperature is constant, this is in reference to a phase change. Temperatures are constant during a phase change. Therefore, between points B and C, the temperature would remain constant. That's where latent heat is being added to the system. Okay. At A to B, where the temperature is rising, or from C to D, where the temperature is rising, this is where you're actually heating up the material. Okay, so maybe what this is here we're heating up a liquid, and now here the liquid is starting to change from a liquid to a gas, and now here we're heating up the gas. Okay, so anywhere where there's a flat line on a temperature versus time graph, that's referring to latent heat. Anywhere where there's a slope to it, we're talking about a temperature change, which is obvious. This is changing temperatures, but we're talking about specific heat. Now, one last thing, and this is kind of a connection to a previous unit. We know that power is work over time. Well, work is a change in energy over time. We're adding energy to do these processes. Okay, so in this unit, we're going to see power is the heat divided by the time, which is simply the amount of thermal energy that we're adding to the system. So this would allow us to, say, solve for the power rating of a heater of some sort. If we know how much time it took here, we could solve using our latent heat equation. Q is ml. If we knew the amount of time from here to here, okay, if we knew the mass of the water and the latent heat of the water, which would be a known factor, we'd be able to solve for the amount of energy required to raise that amount of mass. And if we figured out the time, well, if I knew the amount of heat and the amount of time, then I could solve for the power of that particular object. Okay.